Picture a massive animal. You immediately think of the blue whale. Reaching up to 100 feet long and weighing nearly 200 tons, it dominates our standard mental scale for the modern animal kingdom. To understand exactly how massive that is, consider its tongue. That single muscle weighs roughly the same as an adult African elephant. But measuring strictly by three-dimensional volume leaves out some incredibly strange biology. If we look at pure end-to-end length, prehistoric bone density, or biological connectivity, the blue whale suddenly looks a lot smaller. Our standard definition of size depends on which ruler we choose to use. While the whale captures the title for modern mass, other organisms have evolved to optimize for entirely different metrics of scale. Let's start by looking at one-dimensional length. Plunging into the ocean, we find the lion's mane jellyfish. Its main bell spans 8 feet across, but the real scale is hiding in those glowing orange tentacles trailing behind it. This chart illustrates the difference. The blue line represents the maximum 100-foot length of a blue whale. The orange line represents the tentacles of the lion's mane jellyfish, stretching to 120 feet. That puts the jellyfish 20 feet ahead of our ocean heavyweight. Instead of building heavy muscle and blubber, the jellyfish evolved to sweep the water with enormous, lightweight nets of venom, catching food over massive distances without the energy cost of maintaining a giant body. We can find an even more extreme version of this exact survival strategy hiding out in the shallow tide pools of the United Kingdom. Let's meet the incredibly long bootlace worm. This diagram shows a standard Olympic swimming pool. If you take a bootlace worm and unspool its slimy, ribbon-like body from the starting block, it reaches the opposite end and loops all the way back. That is 180 feet of length, coated in a toxic mucus used to paralyze passing crabs. When you measure strict distance from end to end, the ocean is ruled by extremely long, toxic invertebrates, rather than bulky mammals. If we want to challenge the blue whale on pure weight, we have to travel back 39 million years to look at an ancient marine mammal, Parusetus colossus. Parusetus was shorter than modern whales, but possessed completely solid, rock-like bones. This adaptation allowed the animal to pack immense weight into a smaller frame. Estimates put its mass at up to 340 metric tons, nearly double the weight of a fully grown blue whale. The unique coastal environments of the Eocene epoch allowed these ancient mammals to push the physical limits of bone density, holding the crown for Earth's heaviest creature long before modern whales evolved. We can also change the ruler by looking at how biology defines a single organism. Returning to the deep ocean's midnight zone, we find this massive, glowing white spiral, the giant siphonophore. While it stretches 150 feet long, this lasso functions through the coordination of thousands of interlocking clones called zooids. These modular units link together to form one continuous predatory chain. We can take this concept of an interconnected biological network entirely out of the ocean. To find the true peak of planetary scale, we have to look at the Malheur National Forest in Oregon. Walking through these woods, the only thing you might notice are these small, unassuming brown mushrooms sprouting near the base of the trees. These mushrooms are the only visible evidence of a massive, single mycelial network spreading beneath the forest floor. This specific underground organism covers 2,385 acres, nearly 4 square miles of territory. It weighs thousands of tons, slowly spreading through the soil and digesting tree roots for an estimated 8,600 years. When you redefine what constitutes a single living creature to include massive connected colonies, the largest animals on Earth stop looking like animals and start looking like entire living landscapes. We've measured a 180-foot toxic marine worm, analyzed an ancient whale that crushed the modern weight record, and mapped an underground fungus that eats whole forests. Our definition of the biggest is entirely dependent on our limited human perspective. As soon as you change the ruler you measure with, the natural world reveals itself to be vast and strange. Which of these measurement rulers challenged your view of the world the most?